But this is RTB, Reasons to Believe, which is an international nonprofit corporation or organization formed by astrophysicist Hugh Ross, who became a Christian when he read Genesis in the context of his knowledge of science and found that it was accurate according to his knowledge of science. RTB holds to the proposition that we have the book of Revelation, which is the Bible, and the book of nature as revealed by science, and that there shouldn't be any tension between the two as long as we are interpreting both and understanding both properly. RTB tries to test this hypothesis on a regular basis by keeping up with the latest in scientific research. Sound science, testable truth is the RTB motto. RTB has a robust website at reasons.org that's full of information, books, and resources and videos. You can find the Chicago chapter of RTB on the RTB website at reasons.org, along with the other chapters around the country and in other parts of the world. The Chicago chapter has a YouTube channel, which you can find if you search for Reasons to Believe Chicago. We also have a Facebook page, which you can search the same way to find us. If you've got your computer up, or if you're taking notes or making notes in your mind, I would ask you to go to our YouTube channel and like it. The more likes we get, we have to hit a certain threshold of likes before we can have a unique URL, so we're trying to get to that point. We have past speaking presentations on the YouTube channel, so I encourage you to check it out. And hopefully if we get a good recording of this one, we'll put this one up there as well. Upcoming events in November, we have Pat Perez, who will do a little deviation from our usual science topic with the subject of making sense of mass shootings. And in December, we have a presentation by Dr. Vaughn Mancha on epigenetics. So we'll be back to science in December. Meanwhile, Patrick McGuire joins us today, like I said, from Santa Fe. He's a senior reservoir engineer consultant at International Reservoir Technologies, Inc., with 40 years of energy industry experience. He is a world-class expert in enhanced oil recovery and has designed and implemented advanced oil recovery processes in North America's largest oil fields. He has done energy research for Sandia National Laboratories and Los Alamos National Laboratory. He's authored many technical papers, holds 7 patents, has been a distinguished lecturer for the Society of Petroleum Engineers around the world. Patrick McGuire became acquainted with Reasons to Believe in 1987 when he met Hugh Ross in Anchorage, Alaska. He became the president of RTB Alaska before moving to Denmark in 2009. He has spoken on intelligent design to science and engineering students in China. He's currently working on projects in Alaska, Russia, and the continental United States. So I am going to switch off my audio now and give Patrick a moment to switch over to his PowerPoint, and we'll turn it over to Patrick here in just a second.
So here it is. This is the presentation in English. Recent advances in cosmology and astronomy and their implications. And then we also added the subtitle, Are We Alone in the Universe? This is the famous quote from Carl Sagan: "The cosmos is all there ever was or is or ever will be." And 100 years ago, that made a lot of sense because people believed in the infinite universe. It was infinitely old, infinitely big. Chance alone could cause about anything. You really didn't need God. And the flip side of that is what we've learned in the last 100 years about how the universe really works. And now it's the impression of design is overwhelming. And no discipline has more evidence of that than astronomy and astrophysics. So I thought this would be an effective approach for the students because everybody likes a good detective story. I love watching these British detective shows. And anyhow, we're going to approach it as detectives. We're going to look for evidence, look for fingerprints in the origin of the universe, the design of the universe, the design of our galaxy, sun, solar system, and planet, and then the origin of life. So the sciences involved are cosmology, astrophysics, astronomy, and prebiotic chemistry. And those are what we call the simple sciences, because you can write partial differential equations and solve them and get quantitative answers. And you get into something as complex as evolution or how life evolves on the planet. I'll leave that to Fuzz Rana, because that is so complex. It's difficult to meet my objectives of quantitative proof that design exists. So we're going to open up the universe now, and we're going to look as detectives at which one of these statements is true, that the cosmos is all there is, or that God created the heavens and the earth. And these are the two famous quotes, Carl Sagan or Genesis 1. So the infinite universe, that's where it all started. And from Immanuel Kant all the way through about 1930, scientists believed that the universe was infinite. It was always there, and it was undisputed scientific consensus for 200 years. And it had a lot of observational support. The more we looked out with better and better telescopes, the more we saw, and it all looked like what we'd already seen, only now we're seeing more of it. So there actually was a scientifically supportable consensus that it had existed for hundreds of years, that the universe was infinite. A take-home lesson here is they were completely wrong, but it was consensus based on data for hundreds of years. So who's the guy that overthrew this undisputed scientific consensus? It was this troublemaker named Einstein. And here's his general relativity equation. And I'm not going to go through all this. You can read faster than I can talk. But the bottom line is, this is the equation that governs the performance of the universe, with one little caveat. And Einstein, he realized that his equations basically predicted an expanding universe, which meant if you ran the clock backwards, it had a beginning. He didn't like that, so he threw in this thing called the cosmological constant. And that made the equation be essentially zero, so the universe is neither contracting or expanding. He was unhappy with this addition, but he needed it for his philosophical reasons, to maintain the current status quo. And then another troublemaker came along, and this is Irwin Hubble at his telescope. And in the 1920s, he made these great observations and came up with what we called Hubble's law. And this is the reason that the Hubble Space Telescope was named after him. And what he discovered basically was that the velocity that an object is receding from us is proportional to its distance from us, which basically meant the universe was truly expanding. And Einstein went, oh my God, my original equations were right. I made this horrible blunder with the cosmological constant. So this is kind of how the Big Bang came into being. It's based upon Einstein's original paper in 1915, and then Hubble's measurements in the 20s. And then Einstein, although he was a fairly committed atheist, realized, I'm wrong. There is a God. And he called it the presence of a superior reasoning power in 1930. And a lot of you probably know this, but when you're speaking to students, not everybody knows exactly what the Big Bang is. The best, space isn't exploding. All of our three-dimensional space is like, it's like on the surface of a four-dimensional balloon. And what I've got is a drawing of a three-dimensional balloon with the galaxies all painted on the surface of the balloon, and then you blow the balloon up, and space itself expands. In this case, it's two-dimensional space expanding because it's growing in the third dimension. Well, in our case, the universe is a three-dimensional surface on a four-dimensional expanding system. So that's a pretty good example of, or analog of what the Big Bang really was. It's not an explosion, it's the expansion of space and time itself. And there were a whole series of these things that came out beginning in the 1960s with Stephen Hawking and Roger Penrose, and they're called the space-time theorems of general relativity. And basically, it's a mathematical proof that the universe must have had a beginning if Einstein's general relativity equations are correct. And as T. Ross is fond of saying, general relativity is the best proven concept in all of physics. And this has been extended to cover quantum mechanical models as well as the classical physics models. The beauty about this is they're theorems, not theories. A theorem is a mathematical proof. And I'm sure when you were in high school, your teachers there were not interested in your opinion on the Pythagorean theorem. It's a squared plus b squared equals c squared. You can like it or you can not, but your opinion and my opinion are not relevant. It's a proof. It's a mathematical fact. Well, that was the beauty about the space-time theorems, is it's not anybody's opinion. If you start with equations of general relativity, the universe had a beginning. And they made predictions of, okay, if that's really true, we're going to find this cosmic microwave background radiation. And this is a map of the Cosmic Background Explorer, and it turned this out in 1992. And you may have seen this map before, but this is the map that convinced scientists that, okay, general relativity is right. The universe had a beginning. Huge implications here. 11 years later, this Wilkinson microwave anisotropy probe basically did a much better job of mapping the exact same data. It's just a more detailed map of the same thing. And so, you can ask the question, well, is this background radiation important? And I like these quotes. It's the discovery of the century, if not all time, from Stephen Hawking, the guy that led the project. What we have found is evidence for the birth of the universe. It's like looking at God. So it was really, really, truly important. The universe had a beginning. Now, one of the things that's happened since I gave these presentations in China is I ran into the multiverse there, but there's been a lot of growth in this whole multiverse, the analysis on it. And I'm not going to spend time on it, but I know you guys had Jeff Swearing there. And Jeff's done a great job of studying the multiverse. And I would bone up on this before I actually did this kind of presentation again, because that's the objection I got in China. Number one, we're either unbelievably, incredibly, amazingly lucky. Number two, there's a multiverse with virtually an infinite number of chances, and we're just the lucky one. And it's speculation squared, it's been called, but it's a legitimate scientific speculation. It's based upon what we cannot see, what we cannot observe, and what we will never know. The design in the universe that has a singular beginning is based on what we can see, what we can measure, and what we do know. But it's legitimate scientific explanation, but one is based on data, the other is based on faith. And I just want to make that clear when I was describing the universe or the multiverse. But Jeff does a great job. So what does it all mean? Well, the supernatural exists. Carl Sagan is completely wrong. One thing we know for sure, absolutely for sure, Sagan was wrong. The universe is not all there is. The universe was created. What we don't necessarily know is exactly what created it, but we know the universe is not all there is, and it was created at a finite point in time and space. And this explanation for the universe is not part of the universe itself. The totality, time, space, matter, energy, were created by whatever transcendent cause this is. So if you're going to do science in these disciplines, you've got to deal with the supernatural. So if anybody tells you the supernatural doesn't exist, you can say they're provably wrong. So now we're done with the creation of the universe. It's something beyond the universe created it. Now we can look as detectives at design in the universe. And I want to make this very, very simple. If we're going to be here, it takes four things. We have to have atoms that can combine into molecules. And these molecules that eventually become living things like you and me have to have normal stars like the sun to be around and planets to live on. That's all I'm asking for here. Well, that sounds real easy, but actually it's incredibly difficult. And I love these quotes. There's a number of them, but basically we shouldn't be here. Human existence is possible just because dozens and dozens of the constants of physics, the parameters for the universe itself, lie within certain highly restrictive ranges. And the more we've learned about this, the more amazed we've gotten at how tight these parameters are. And there's four fundamental forces of physics, and I'm going to go through a couple of them, but it's gravity, the strong nuclear force, the weak nuclear force, and the electromagnetic force constant. And we're going to just look at a couple of these. The strong nuclear force, that's what holds the protons and the neutrons of a nucleus together. So like protons, they have the same charge, they want to fly apart. Neutrons don't have a charge at all, but you put these guys together, and if the strong nuclear force is just right, you've now made an atom. And if the strong nuclear force was 2% weaker, these protons would never come together, and all you'd have in the universe is hydrogen. And you're not going to have anybody to talk to in a universe with only hydrogen. But if it was, and I like this, 0.3% stronger, there would be so much holding these nuclei together that basically you just have stuff heavier than iron. You wouldn't have any of the light elements like carbon and oxygen and nitrogen and stuff we're made of. And you'd also just have neutron stars and black holes. So the strong nuclear force has to be just right. The electromagnetic force is another really cool one. And that's because there's a lot of things that you need the EMF to be right for. But if it was 4% weaker, then the electrons, instead of orbiting the nucleus, they would just all be free. You wouldn't have any chemistry whatsoever. And then another thing they found out was, well, gee, we wouldn't actually have any carbon or hydrogen available for planets. They would all be stuck inside stars. So the EMF's got to be, got to be just right. And if it was 4% stronger, this is really kind of cool. Chemistry happens, if you recall in high school, you can have ionic bonds, but what really makes chemistry is what are called covalent bonds when two different atoms share electrons. And that's what makes, for example, carbon dioxide possible, because this carbon and this oxygen are sharing electrons. But if it was 4% stronger, none of these atoms would be sharing anything. They'd just be hanging on to their own stuff, and we wouldn't have any chemistry at all. Now, there's lots of other things, like, for example, the carbon or oxygen escaping, supernovas again. The EMF has to be just right. And there's other things like fine structure constants and the other part, the forces of physics, that I'm not gonna go through. But we see design in a lot of different levels. This is actually my favorite, because they looked at how the universe expanded based upon the general relativity equations. And if the mass density of the universe was changed by more than 1 part in 10 to the 60th power, you wouldn't have life in the universe. If this mass density was just a little bit bigger, everything would collapse into neutron stars and black holes before it got expanded. If it was just a little bit less density, then gravity's not strong enough and everything spreads apart so fast, you don't form stars. And 1 part in 10 to the 60 is it's a number. I can't wrap my head around it. But I'm from Alaska, and I've swatted a lot of mosquitoes when I've been out fishing and stuff, or hiking. And every one of these little guys in the universe that we can see, there's like 1 trillion galaxies or more. And on average, these galaxies have 100 billion stars. And if you were to look at that mass and all that mass in the universe, 1 part in 10 to the 60th of that is the mass of a mosquito. So if there was 1 mosquito less in the entire universe that we could see, we're dead. And that's pretty amazing stuff. But that's not the best. The best goes back to that cosmological constant that Albert Einstein threw in his equation. He actually was right. There is a thing, we call it dark energy, but it's essentially the cosmological constant that's driving the expansion of the universe. It was only discovered, gosh, about 20 years ago. And we've learned a lot more about it. We don't know what it is, but we know it's driving the expansion of the universe. And this is the most extreme fine-tuning problem known. So it has to be tuned to within 1 part in 10 to the 120th power. And I just can't grasp that number. But what I've shown in yellow here, the yellow is the number of protons in the universe, and the white stuff is like, I don't know, 100 billion times the number of protons in the universe. That's how precise this fine-tuning had to be. That's pretty amazing. So what did the guys do when they ran into this? Well, there's some great quotes here. And if I was to do this presentation again, I would update some of the quotes just to get a later year on them, but nothing's changed. Arranging the universe as we think it is arranged would have required a miracle. And again, these are people from like MIT and Stanford, and these are like some of the sharpest scientists and astrophysicists around. I like this guy, Arno Penzias. He's a believer. He won the Nobel Prize in physics for his discovery of the cosmic background radiation. And his conclusion: a universe with a very delicate balance needed to provide exactly the conditions required to permit life. Fred Hoyle, this guy that came up originally because he hated the Big Bang and he was determined to overthrow it. Later, he's the one that actually gave the terminology Big Bang it was a term of ridicule. But as he learned more and more and more, this was his quote: "The super intellect has monkeyed with physics as well as with chemistry and biology, because he made a number of the discoveries on fine-tuning." So that's the second of our two: the origin of the universe, now the design of the universe. And now we're going to get into my favorite piece of this. And it's called the design of our galaxy, sun, solar system, and planet. And this is my favorite because there's fingerprints all over the place when you start looking at the astronomy for how we could actually exist as human beings on planet Earth. And I think Hugh Ross would say right now there's probably over 600 parameters, but I just made it real simple when I presented this and said there's over 100 parameters that require exquisite precision. We have to have the right galaxy, the right star, the right location in the galaxy. We absolutely have to have the right Jupiter. We now know, for example, we have to have the right Saturn and all as well, but I didn't go into that then. We have to have the right Earth and the right Moon. All of this has to be just right for us to have a habitable planet. So let's take a look at some of the stuff. And I'm giving an example here of we have to have a high metallicity star. To an astronomer, a metal is anything heavier than hydrogen, or heavier than helium. And the first generation stars, which is most of the stars in the universe, that were formed after the Big Bang, they had hydrogen and helium, and that's like it. Tiny bit of lithium, maybe a baby amount of beryllium, but just next to nothing. And you can't do anything with hydrogen and helium. If you could make a planet at all, it would be a gas giant, no surface, no hope of life of any sort, no hope of chemistry of any sort. And what adds the metals to the stars is supernovas. They blow up and they distribute their heavy elements that they've manufactured by fusion out into their galaxy, and then new stars can form from that gas. And these new stars now are going to contain heavier elements, and these heavier elements can also be involved in the formation of planets. Well, it turns out you actually need three generations of stars before you finally make enough to make a rocky planet. So most of the stars in the universe just don't have enough stuff to make rocky planets. So that's just one of the many design elements. So let's now take a look at the big picture. And you've got to be in a small, isolated galaxy cluster. And because we have our Milky Way, and then way off 2 million light years away, we have the Andromeda galaxy. We sort of view that as normal, but it's not. That's very, very unusual. Most galaxies occur in these gigantic clusters. And these gigantic clusters, there's lots of bad stuff going on, but in particular, they got gravitational exchanges that disrupt what's called the habitable zone in the galaxy. So and there's lots and lots of lethal radiation going on. So these big clusters are really not a place you're going to find life. And also when they're close, things collide a lot. When Milky Way collides a lot with other galaxies, but they're a lot smaller galaxies, so Milky Way eats them. And that's really important for us. A big galaxy hitting a big galaxy, that's a train wreck. That's really bad. Well, it turns out only about 1 galaxy in 1,000 is in a safe cluster. That's pretty big number, 1 in 1,000. You got to have the right kind of galaxy too. It's basically got to be a spiral galaxy. And elliptical galaxies in particular, like this big M87 right here, it's a huge galaxy, huge. But it's basically not forming any of the right kind of stars. Its star formation quit billions of years ago, and they just don't have the right kind of stars for making planets. So if you find an elliptical galaxy, and that's what most of them are at this point in time, it's really not a candidate for life. You need something that looks like us or our neighbor Andromeda, but only about 6% of these galaxies are spirals. So now you're down to less than 1 in 10 again, like 1 in 15. Here's one that's even more important. You've got to have a bachelor type G star in order for you to form a planet that we could live on. And basically, big stars like these class O, Bs, and As and Fs, they're far too unstable. They're short-lived. You know, the bigger the star is, by far the faster it burns up. You know, things expand, radiation intensifies. They're very, very unstable. And so you need one of these yellow class Gs like our sun. And if you're a small star, and we'll see why in a minute, but if you're in the small stars like the class Ms or Ks, they're not candidates for life at all. You have to be way too close to these things because they're so dim, and then other things will kill you. So again, 1 in 1,000 of the stars in the Milky Way is main sequence class G. And this is what's called a Hertzsprung-Russell diagram. I never pronounced that right. And this is basically as a function of the mass of a star, its stellar classifications. Big stars are very, very bright. For example, that's 10 to the 6. That's 1,000,000 times more luminous than the sun. And these are very big. They're very bright. They're very unstable. Most of the stars in the galaxy and in the universe are these class M's, these red dwarfs. And our sun here is this class G. You know, we're at one solar luminosity, 1 solar mass. So everything's normalized to the sun. Well, what happens, especially with these small stars, this is where we found most of the planets in the like the Kepler Space Telescope. Most of the planets we've discovered orbit around these small stars, and they're easy to spot planets around because you know, planet goes in front of it and it blocks out the light, and you know, if the planet's reasonably sized and the star's not that much bigger, you get a big signal. And so we've discovered lots and lots of planets around these kind of stars. But what the problem is the luminosity is basically roughly proportional to the size of the luminosity of the star, which is controlled by how massive it is. If you're going to get the right kind of energy on that star for maintaining liquid water, it's what's called the inverse square law. the energy you're going to need is proportional to the radius between the planet and the star squared. What that means is a dim star, you've got to get really close to it. And but what gets really bad is the tidal forces. These are the things that stop the planet from rotating. Kind of like what the Earth has done to the moon. The moon is tidally locked. It only presents one face. So when it goes around the Earth, we only see one side. Well, that happens to planets because instead of 1 over r squared, the tidal forces are 1 over r to the 4th. So if you've got a 0.3 solar mass, which is like in here, and I'll show you an example of one. It's you know, this maybe a class K or maybe a class M star, but the tidal forces have gone up by a factor of 3,000, which basically means these absolutely these planets are not going to rotate, or if they rotate at all, it's going to be in what's called a synchronous rotation. It's not going to have a normal kind of a day at all. It's going to have something very, very long. So people can debate as to what's the most Earth-like planet ever found. Back when I was presenting this Gliese 581c was advertised as the most Earth-like planet. It was right in the middle of its habitable zone, and people got very excited about this. So here's the sun right here with 1 solar mass. This little star, it's 0.31 times the mass of the Earth, and here it is, and it's the planet is right in the middle of the habitable zone, and that's wonderful. But when you look at the tidal forces, they're higher by a factor of 10,000 than the tidal forces on the Earth. And if we were 10% closer to the sun, we'd probably be tidally locked as well. So this planet is definitely tidally locked. It faces its sun, never moves. So the one side gets hot, hot, hot. The other side gets cold, cold, cold. And it's got no rotation. It's got no magnetic field, and it's super close to its star. And these small stars are very, very unstable. They have these huge flaring events. So you're like looking down the barrel of a shotgun at point blank range, and they're pumping shells at you multiple times a year. Like in the case of a lot of these class M suns early on, they're very unstable. So you just get blasted again and again and again and again and again with these huge solar flares, and you've got no protection at all, and you're at point blank range. So these planets likely have no atmosphere at all, unless it's very, very dense, in which case, and this planet was going to have a dense star or dense atmosphere because the mass of the planet was 5 times the mass of the Earth. So they used to call them super Earths, but they're starting to call them now mini Neptunes. It's going to be a very, very dense atmosphere. They now estimate the surface temperature of this planet is like Venus. It's 400 centigrade, 900 or 800 Fahrenheit. It's no life ever on a planet like this. This is the best one they had. And this typically is what's happening when we start looking at these class M suns. So you've got to have the right star. It's got to be a class G, and the star has to be in the right location. And one of the volunteers for reasons to believe is a guy named Guillermo Gonzalez. He's an astronomy prof. He was at Iowa State. I'm not sure where he's at now. But he came up with this concept of the habitable zone, the galactic habitable zone. And I like the title of the Scientific American magazine here. Outside a ring of stars, galaxies are hostile to life. So you've got to be at the right location in the galaxy. And basically, if you're anywhere near the core, you're getting bombarded by huge levels of lethal radiation. So there's not the proverbial snowball's chance in a very hot place that you could survive anywhere near the galactic core. And the same thing is also true of the spiral arms. There are just all kinds of bad things going on there. And if you're too far out, if you're out here in the weeds, then you don't have enough of these metals to make rocky planets. So you've got to be in this fairly narrow zone. And this is a representation of the galactic habitable zone, and it really is narrow. It's got to be close to this what's called a co-rotation circle, which is where the rotation of the planet or the suns that are going around is about the same as the rotation of the spiral arms. Anyhow, it's a very narrow region within the galaxy that you can actually have life. And that's not just in two dimensions, looking at it down like you're looking at a vinyl record or a CD. It's also got to be the right location in the Z direction. And again, there's all kinds of lethal radiation pouring out of the galactic bulge, and then all of this this dust and gas in the plane of the galaxy. Those are like the shield walls on a nuclear reactor. And if you don't have the shield walls, you're gonna absorb lethal amounts of radiation. So you've got to stay hidden behind this this galactic plane, or the galactic bulge is going to kill you. And a lot of stars, when they orbit, they go up and down, and they go outside of this blast wall protection. And actually, even the Earth, we've apparently suffered mass extinction events by going beyond this, poking our head up a little too far. And it's obviously, it's not a single line. The farther you get, the more you're going to get exposed. But we apparently have had enough exposure to cause mass extinctions on the Earth as the sun has moved around the galaxy. So you got to have the right star, you got to have the right galaxy. Now this is really cool. I remember when this happened back in 1994. You've got to have the just right Jupiter to shield you. And this comet, this Shoemaker-Levy comet, it orbited around Jupiter, and Jupiter tore it up into like 21 different pieces. And then the next time it came around, these pieces all went into Jupiter, and just wham, 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 wham. That just kept hitting. And I believe it was the Galileo spacecraft was actually filming all this as it happened. Great pictures. One of the RTB guys was actually involved in this whole Galileo mission. It was pretty cool. But the energy release from the Shoemaker-Levy comet striking Jupiter was 100 million megatons of TNT. And that's 10,000 times the yield of all of the nuclear weapons on Earth combined. And that's just one comet hitting. And if that would have hit the Earth, that's game, set, and match for life on planet Earth. We'd have all been dead. All life on the surface would have been dead. And we watched this in 1994. And I love this quote from this guy named George Weatherall, that without Jupiter, just where it is and how big it is, the Earth will be struck about 1,000 times more frequently than it is already. And he said, if it were not for Jupiter, we wouldn't be around to study the origin of our solar system. I thought that was a great quote. But what you're looking at here is these plumes, these dark bruises on Jupiter. They're each larger than the Earth. So these were massive impacts, just 21 of them. And again, if this was happening 1,000 more times, the thing that killed all the dinosaurs 60 million years ago would be happening every 60,000 years instead of every 60 million. Well, there's no way advanced life could possibly survive that kind of assault. So again, we wouldn't be here. And if Jupiter was any larger than it is, or any closer than it is, its gravity would actually rip the Earth out of its stable orbit. And if Jupiter's orbit wasn't very, very circular, if Jupiter had an elliptical orbit, it would also disrupt our orbit. But if Jupiter was farther away, or it was smaller than it is, it just wouldn't be a very effective shield. So now we've got the right kind of galaxy cluster, the right kind of galaxy, the right kind of star, the right kind of Jupiter. Now let's take a look at the atmosphere of the Earth. The atmosphere of the Earth originally was probably way thicker than it is now, probably much more like what's currently in Venus. And if we had a thick atmosphere like Venus, we would just fry it. There wouldn't be any water, there wouldn't be any life, there wouldn't be anything here. Jupiter, or excuse me, Venus is 90 atmospheres, 470 C. That's almost 900 Fahrenheit. There's no water anywhere on Venus. If our atmosphere was thinner, like Mars is the 100th of our atmosphere, our surface temperatures would be so low, we would be an ice planet. There's be no water, just ice, no life. And then the other thing, we have to have ozone. And without our ozone layer, we would be experiencing deadly levels of ultraviolet radiation. UV radiation is what we use to sterilize surgical instruments. We would die in a big hurry without the ozone layer. And so how do we get this this beautiful atmosphere that we've got? Well, we have to have a just right liquid iron core. Because what we need a long-lasting, strong magnetic field to protect us from the solar wind. And the solar wind are charged particles, in particular protons, that are going at some significant fraction of the speed of light. And basically, if those things were hitting our atmosphere, they would just do what they did to Mars. They just knock the atmosphere away. And so if you want to keep an atmosphere, you've got to have this just right liquid iron core. Another thing one has to have is you have to have the right rotation period. And you know, the Earth 4 billion years ago was our day was about 4 hours long. And with a 4-hour day, your atmosphere had incredible wind velocities. So your afternoon breeze, for example, instead of being 20 miles an hour, it might be something like 3,000 kilometers an hour. So there's no way any kind of advanced life could survive these kind of incredible winds. But if it was rotating, let's say we had a 30-hour day, then the difference between night and daylight temperature would make life almost impossible. So we've got this just right 24-hour rotation. And what gave us this 24-hour rotation is our moon. We have to have just the right moon. And the Earth-Moon system is really pretty unique. There's nothing else like it in the solar system. This impact event that made the moon removed our early atmosphere, which was probably a lot more like Venus's. And so without the impact that made the moon, Earth would not be a place for life at all. Also, another thing that happens is the Earth's rotation axis is at about 23 degrees, and it varies just a little bit because the moon is like an outrigger on a Hawaiian canoe. It's a big, massive body, and it keeps our orbit from doing weird things. Mars, on the other hand, it can rotate, to like 60 degrees, anywhere from 0 to like 60 degrees. It has huge impacts on your climate. And also, our moon was required. Without the moon, we would not have plate tectonics, and that's absolutely required for longevity for life on Earth. So how did this moon get formed? Well, there's still a lot of debate on the specifics of it, but basically it required this perfect collision with a Mars-sized planet. So this isn't a comet or an asteroid. This is another planet hitting the early Earth. It's actually got a name. It's called Theia. And this perfect velocity, there's debates as to exactly what it was, but it appears that it might have been a 45-degree kind of a glancing blow instead of head on. If the impact was too big, it would have just blown the Earth apart. We'd all be gone. But what this perfect impact did is it removed our thick, suffocating early atmosphere. It enriched the core in radioactive elements like thorium and uranium and heavy metals. And that's what has enabled us to keep this lovely magnetic field for 4 billion years. And then it made our crust a lot thinner. And a lot of that crustal material now is the moon. And now the crust is thin enough to actually have plate tectonics and things subduct under other plates. And so this collision had to be absolutely right. So now you can, and I've just gone through just a few of these things, but you can actually go through the math now. I love this because it's quantitative. So let's take a look at maybe some of the odds of us having the right kind of place. So you got the right galaxy, the right numbers of supernovas, The parent star's got to be at the right. It's got to be at the co-rotation distance. You have to have, for example, the right star mass. That's 1 in 1,000 is the right mass. But you can put numbers to all of these, and that the specific numbers aren't important. You put your own numbers in there if you wish, but you can do this and come up with a probability calculation. I've got a bunch more numbers here. Some of these are, you got to be just the right distance from the parent star. You've got to have a long-lived magnetic field. You've got to have for example, here you got to have the right Jupiter, and you can put all these things together, and you can realize that, okay, not all of these are purely independent variables. You've got some overlap. So we're gonna multiply the odds by, in this case, 1 billion. But you've also got to maintain these kind of things for a long period of time, because we're here not because conditions are right 4 billion years ago, but because conditions are right now. So you got to maintain these conditions for a long time. Anyhow, you do the math on just these 24 parameters, and there's hundreds and hundreds of them. But just for these 24, the probability for obtaining in our entire universe, we've got 10 to the minus 32 here for all of these parameters to be right, a maximum number of 10 to the 22 planets in the entire universe. And that gives us the probability of one habitable planet occurring in the entire visible universe is 1 in a billion, less than 1 in a billion. So even with only 24 out of hundreds and hundreds of these parameters, there's no way we can be here by chance. No way. And again, I encourage people to put their own numbers in there, run their own calculations, and you will come to the same conclusion. So there's only really 2 options. Number 1, we were incredibly lucky, or number 2, we're supposed to be here. But you do the math, and that's the beauty about this, it's quantitative. Either you're lucky and unbelievably lucky, or we were intended to be here by whatever created the universe. So what do people say? Well, I've got some quotes here. You could come up with thousands of quotes, but these are some of my favorites. There is, for me, powerful evidence that there is something going on behind it. The impression of design is overwhelming. Here's the guy. This guy got a Nobel Prize for inventing the laser. He's a seriously bright guy. It seems to me that when confronted with the marvels of life in the universe, one must ask why and not just how. The only possible answers are religious. I find a need for God in the universe and in my own life. So we've done 3 out of 4 of them now. We've got one more to do, and that is the origin of life. Again, we're going to be detectives. There's 4 key issues that I'm going to cover on the origin of life. One is the primordial soup, and everybody that's ever been in a science class in high school heard of the primordial soup, even though it didn't exist, and you'll see that. The time available for this primordial soup to make life, and then a thing called homochirality, which is basically handedness. And my left hand is similar to my right hand, but it's not the same. They're different. There's a left hand and a right hand. And that's absolutely essential in biological systems. That's called homochirality. And then complexity. So we're going to look at each one of these 4 and see how that affects as detectives, how that affects the probability of life occurring by chance. Now, again, if you graduated from high school, you doubtless heard of Stanley Miller's experiments in the 1950s, the spark discharge, where they put this glass cell in here, ran voltage sparks through it, and collected stuff in the bottom, and all the implications on the origin of life. So this is a picture of Miller when he was like a grad student, working for a professor named Harold Urey, and now he's a lot of years later. He's got a lot less hair, and this is the original device. The spark chamber with the atmosphere, and then collect the junk at the bottom. And so here's a schematic of what it looked like. You've got your boiling water, and then this water vapor is coming up in here. You've got an atmosphere that contains methane, CH4, ammonia, NH3, and hydrogen, H2. And then you shoot sparks across all this. And this is supposedly going to represent the early Earth's atmosphere. And then the water condenses, all this stuff comes down to the bottom, and you collect this goop and you analyze it. This is the actual reaction vessel, and then the trap, and there's the actual hardware. The key thing to notice here is, what are the gases that he's assuming were representative of the early Earth? And then what are the products that were formed? Well, if you ever cleaned a crap off of your barbecue grill, most of it was exactly that, barbecue tar. It's useless for anything. There's nothing you can do with it. There's no way it can participate in the chemistry of life. It's just tar. There were 15% of it were organic molecules. Formic acid's bad stuff. But the amino acids that were formed in this, two of them, glycine and alanine. And so this experiment did indeed form amino acids. And amino acids, which are also called the building blocks of life. Well, this is glycine, and this is alanine. And basically, you've got like this, for example, right here, this blue molecule, that's a nitrogen. So you got a nitrogen with two hydrogens. You got a carbon, and this is what's called a carboxylic acid group. You've got a carbon with an oxygen and then an oxygen hydrogen. This is an acid group. But this thing has 10 atoms in this molecule. This is not a complex system at all. This is what I call a biological rivet. These are very, very simple molecules. Yes, they are the building blocks of life, but these are rivets. And believe me, when you've got a couple of rivets, you're a long way from the space shuttle. And that's really what life is like, is the space shuttle. So again, you've got a 10 atom molecule, and then the incredible complexity of living systems. So you just need to keep in mind, when you hear building blocks of life, think rivets. So now, are these experiments relevant at all? Well, here's the quote from Stanley Miller. We believe that there must have been a period when the Earth's atmosphere was reducing, and that means it's hydrogen rich, because the synthesis of compounds of biological interest take place only under reducing conditions. And that's a true statement. The trouble is, this reducing atmosphere that he used never existed. It never happened. There was never anything like methane, ammonia, and hydrogen. You might get that on the planet Jupiter, but you never got that on planet Earth. The early atmosphere was carbon dioxide, nitrogen, and water vapor. It was an oxidizing environment, not a reducing environment. So the chemistry is impossible. No biological or biomolecules can be formed from that spark discharge kind of experiment. And origin of life scientists now agree these experiments really are irrelevant. There's another big problem on the early Earth, because I kept hearing things about the warm little pond. And so you'd have, the tides would come in, and then there'd be water there, and it's nice and warm, and the sun's shining, and things dry out, and then the tide comes back in, and you concentrate these organic things in these little warm ponds. Lots of physical impossibility. It never happened. Because what happened was, again, the Earth's rotation day was about 4 hours long. The afternoon breeze was several thousand kilometers an hour. So let's call that 2,000 miles an hour. And I mean, Hurricane Ian just went through it, max winds of 150. That's absolutely nothing compared to what the early Earth was like. And the daily tides, it wasn't this couple of feet gentle slosh back and forth. These tides were maybe 1 or 2 kilometers high. They were monstrous, multiple kilometers. And then this is happening. You've got low tide at 1 o'clock, high tide at 2 o'clock, low tide at 3 o'clock, high tide at 4 o'clock. This is happening all the time. Meanwhile, the wind's blowing thousands of miles an hour. So what you need to think of on the early Earth is this is a blender here. So you put some water in this thing and turn it on its highest speed setting. That was the early Earth. There's no way you're getting a warm little pond. It's an incredibly violent, hostile, well-mixed world. So a lot of these suggestions of how life originated were simply not possible on the early Earth. And I said, well, okay, you can't get anything at the surface. There's no such thing as a warm little pond. It must have been a submarine vent, volcano coming out the bottom of the seafloor. But one of the troubles with that whole theory is the half-lives of these life molecules. They're, I mean, even at 100 degrees C with 212 Fahrenheit, these things are in years to days. At 350 C, which is a more representative temperature, these things die in a few minutes, and the nucleotides, the things that make up our DNA, those things dissolve in seconds. So it's and the RNA that was hydrolyzed within minutes, seconds to minutes. So basically, submarine vents destroy, they don't create. So when you actually look at it and do the math, and you start cycling the Earth's oceans through submarine vents, it destroys all of these chemicals. So Stanley Miller, again, this guy that had been working this forever, they came up with this conclusion. Unless the origin of life took place extremely rapidly, in less than 100 years, we conclude that a high temperature origin of life, in other words, submarine vents, cannot involve adenine, uracil, guanine, or cytosine. Those are the nucleobases that make up RNA. So basically, you can't do this stuff on the surface. You can't do it in a submarine vent. And there's another problem with the early Earth. And this one is real. I've never heard anybody address this because I don't think it's possible to address it. Is that in all these experiments that are done, they use like distilled water. Well, I mean, it's very pristine laboratory conditions. Well, in the real life world was nothing like that. The early oceans were absolutely loaded with rare earth and heavy metals. It was like a super fun dump site. It's incredibly toxic. And some of the chemicals here, I mean, there were like, it was loaded with iron, lead, zinc, cadmium, selenium, chromium, arsenic, and others. It was a horribly toxic environment. And basically, nothing on planet Earth, except for a few highly specialized bacteria, can survive in that kind of environment, because these particular bacteria, they have biochemical systems that allow them to isolate all of this horrible multivalent poison from their biological machinery. But if you don't have that specialized bio machinery, then this stuff just totally destroys organic compounds. It's I've never heard of a successful argument for why this isn't devastating to the concept of origin of life. Now, here's another one, and that is the prebiotic soup. And everybody's heard of it. This is this nice, rich bath of organic materials that that combined gradually over millions of years and became more and more complex, and then all of a sudden life appears. Well, the neutral atmosphere that we had on planet Earth back when life originated can't form biomolecules. There was no formation on planet Earth of biological building blocks. The extreme winds, the warm little pond that concentrates stuff, that was physically impossible, couldn't happen. Another one that's really bad is ultraviolet radiation, which is what we use to sterilize bacteria. And we have to be very careful because it can sterilize us as well. It destroys life molecules on the surface. And you're stuck with one of two things. It's called the oxygen UV paradox. You've either got oxygen in the atmosphere that allows you to form an ozone shield, and that protects you from the ultraviolet, And then it's the oxygen that destroys these prebiotic molecules. So you're either destroyed by oxygen or you're destroyed by ultraviolet radiation, and there's really not a plausible way out of that. And then submarine vents destroy life molecules. So the stuff never existed because it couldn't exist. The other thing is, it's never been found. And I'm a petroleum engineer. I deal with postbiotic soup, you might call it that. Oil is kerogen that has been converted into stuff that we can make gasoline and diesel out of. And there's oodles of that all over the planet, but it's all postbiotic. We have never seen a trace of anything prebiotic. So it's not like we don't see it because it's not stable. The stuff I work with is hundreds of millions of years old. It's stable, but it was all created by biology. And then here's another really interesting one. It's called the late heavy bombardment. And in back about 3.9 billion years ago, the Earth had the solar system had a Kuiper belt that looked kind of like this. This is the sun is in here, and then you've got like Jupiter, Saturn, Neptune, Uranus. You've got the gas giants in here. And then what happened was Jupiter and Saturn got in this harmonic orbit, and they started really screwing things up. So you started dispersing this Kuiper belt. Then you eventually shoved Neptune, Uranus and Neptune changed places. And this stuff just got thrown everywhere. And a lot of this stuff came into the inner solar system. And now what we've got left is just a trace of what we used to have. But basically, this harmonic between Jupiter and Saturn hitting the same place with every time they went around, they disturbed the outer solar system, and all this stuff came in, and basically the Earth and the Moon, the inner solar system, took an incredible hit. And when this is the surface of the Moon, and that's when all these craters basically happened, was in this late heavy bombardment. And the Earth took a lot more hits than the Moon. So the Earth looked just like this too, except we had an atmosphere. So this would have been kind of a schematic of the Earth about 4 billion years ago, about 3.9 billion years ago. And nobody knows for sure, but it appears that the surface of the Earth was molten to a depth of about 200 kilometers. Organic molecules could not possibly survive anywhere on planet Earth, surface or subsurface. We don't even have rocks from this time frame. Zircon crystals survive because they're basically like miniature diamonds, but no rocks survived. And these were the estimates. Again, we don't know for a fact, but these are estimates. But tens of thousands of craters with diameters greater than 20 kilometers. I like this one, several impact basins with a diameter of about 5,000 kilometers. That's basically bigger than the United States. So you've got holes in planet Earth that are bigger than the United States. I mean, these were hits. These were serious, huge hits. So this is basically reset any possibility of life on Earth. And then that happened 3.9, 3.8 billion years ago. So as soon as the lava congeals into rock and we start getting liquid water on the surface again, that's when we find life. There's no time for this to happen. The oldest sedimentary rocks ever found contain life, and that's based on the carbon-12 to carbon-13 ratio. Life molecules like to process carbon-12 more than carbon-13. And this has been amazing to a lot of people. Niles Eldridge, who's a very, very famous guy, had this great quote. One of the most arresting facts I've ever learned is that life goes back as far in Earth's history as we can possibly trace it. In other words, in the very oldest rocks that stand a chance of showing life, we find those signs, those vestiges of life. So how long did life have to emerge? The answer is it emerged essentially instantly. So now we're going to look at a thing called the homochirality, which is the right-handedness and the left-handedness. And this is this simple molecule where we've got a left-handed form and a right-handed form. And there's no way to get these guys to look alike. They're truly different. And interestingly enough, we have no way of generating what's called homochirality, which is all one direction or all another. But biological systems can do it. And life uses only left-handed amino acids and right-handed sugars. And life absolutely requires homochirality. And we don't know, other than living systems, we don't know how to do this. And one of my favorite examples of this is looking at the right-handed and left-handed nucleobases. So for your DNA, it forms a helix, but it's like the rungs of the ladder. So you've got a backbone here, and then you've got an active group, a functional group sticking out. And here you've got a backbone and then a functional group sticking out. And if these are oriented right, you have a living system that has a rung on a ladder. But that's one combination out of four. This doesn't work because both of them are pointed left. This doesn't work because both of them are pointed right. This doesn't work because they're both pointed out. So you've got no rung of the ladder. You've got no DNA helix. You've got no life based on DNA unless you've got the homochiralic system. They've got to be right. And again, 3 out of 4 of the combinations leads to death. And this was an interesting quote. This guy in Stanford, William Bonner, was the world's leading researcher on how to generate homochirality. And his quote is just brutal. I spent 25 years looking for terrestrial mechanisms for homochirality and trying to experimentally investigate them and didn't find any supporting evidence. Terrestrial explanations are impotent and non-viable. And that's where we currently stand today. So the last one, and I'm getting close to the end here, so be patient, you're almost done, is the incredible complexity of life. And living systems, and these are systems that don't even have to generate their own living. They just live in this primordial soup and eat stuff that's available to them. And an average of 400 amino acids in a distinct order are required to form a single protein, and in a minimum cell, 239 proteins of at least 124 different types are required. So, and this is from this molecular biologist, Harold Morowitz. And it's like, this is incredible complexity. This is not a 10 molecule or 10 atom biological ribbon like glycine. This is what's really required. And every cell in your body's got cytochrome C. And this other guy, Yaki, they like, he's called Dr. No because he tells it like it is. This very simple protein, I mean, only 110 amino acids. And he's done this estimate of what it would take to form even one of these, one functional cytochrome C by chance. And it's a whole bunch of acceptable planets for a billion years. I mean, there's no way this is happening by chance. And his quote here is brutal. Could these things have combined by chance into functional molecules, functional protein molecules? Although at the beginning the paradigm was worth consideration, now the entire effort in the primeval soup paradigm is self-deception on the ideology of its champions. And that's for a lot of different reasons, but it's and this is an old quote, but it's still true today. Without the hypothesized atmosphere and medium for life's self-assembly, materialist assumptions stand without any basis in reality. We can find no evidence to support, only evidence to contradict a gradual sequence of primeval events and conditions leading to the spontaneous generation of life. So again, what we have, to summarize it, we have an intractable problem. It's essentially impossible to the fourth power. It's impossible times impossible times impossible times impossible. The primordial soup absolutely did not exist, and it couldn't have existed. And that's why we don't find it, because it didn't exist. It was a virtually instantaneous appearance of life after the late late heavy bombardment, the oldest sedimentary rocks ever discovered had life in them. And we have no mechanism known that we can generate this homochirality that's required by living systems. And we have no mechanism, no plausible mechanism for generating the kind of information that's required for living systems. And the more we learn, all four of these problems are getting worse and worse and worse. So, final conclusions. The origin of the universe. It did have an origin. Space and time were created by something outside this universe. The supernatural exists, and you've got to deal with the supernatural if you're going to do science and like physics, cosmology, and astronomy. You can't use the thing that, well, we can't examine the supernatural. Science doesn't do that. No, if you're going to do science, you're going to have to do that. The design of the universe, unbelievable fine-tuning in the fundamental physics of the universe itself. The evidence for design in astronomy, unbelievable amounts of precision in both the type of galaxy, the type of star, the location in the galaxy, the right moon, the right Jupiter, the right Earth. It's unbelievable evidence of design from what we can actually measure and calculate. And then the origin of life, we have no explanation, none, for the origin of life. Nothing that's plausible at all if you honestly look at it. So what do we do with all this? Well, there was a guy, his name was Anthony Flew, and he was in his 80s here when I think this picture was taken. And he was a dedicated atheist. He spent his life basically promoting atheism. He wrote these books, one after another on atheism. And now he was a former atheist because he looked at all of this and thought, my God, there is a God. And his quote was, I had to go where the evidence leads. And again, his quote, I think the most impressive arguments for God's existence are those that are supported by recent scientific discoveries. And here's another guy, won the Nobel Prize in Chemistry for his work on these carbon systems. And he met with Hugh Ross, president of RTB, back in 2004, and he became a follower of Jesus. And wow, this is a smart guy. So you can be a smart guy and believe in God. That's the whole premise here. So final conclusions. A transcendent cause created the universe. Something beyond the universe itself made this universe we live inside of. The evidence for intelligent design on everything we can see and measure and calculate, it's overwhelmingly evident for design. And this evidence is growing stronger and stronger and stronger the more we learn. So the conclusion is becoming more sound. And my final premise, atheist is no longer consistent with modern science. You can do that by faith, but it's an exercise in faith, not science. So this is what I ask the university students to do. Do good science, ask good questions, examine the data carefully, and then do what Anthony Flew had the courage to do in his 80s. He spent his whole life as an atheist. Go where the evidence leads.